Hey everyone, let's get started here. Thanks for joining us today. My name is Jason Key at SP Grid at Harvard Medical School. Today we have Peter Eastman joining us. Peter is in Vijay Panda's group at Stanford. He's a senior software engineer there, and he's going to be telling us about OpenMM. Peter, are you there?
There I am. Can you hear me?
I can.
Excellent. All right. Well, thanks a lot for having me. And can everyone see the slides?
Looks good.
Okay, excellent. So yeah, I'm going to be talking about OpenMM, which is the molecular dynamics software I develop. Feel free to ask questions at any time as I go along. So let's see what this, sorry, there we go. OpenMM is a toolkit for high performance molecular simulations. And it's really, in many ways, quite different from pretty much any other molecular dynamics toolkit out there. It consists of two main components. First of all, there's a low-level computational library. It's written in C++, although it uses within that then lots of other technologies like CUDA and OpenCL. And that is where most of really the high value parts of it live. All the computational parts for evaluating forces and doing integration and all that sort of thing. And it can actually be used directly as a C++ library that other applications can link to. But then on top of that, we have what we call the application layer, which is written in Python, and that sits on top of it. It uses the C++ library, but it adds all the other features that you would need for actually running simulations, things like the ability to load PDB files or to write out trajectories and all that sort of thing. OpenMM is designed to be kind of a hardware abstraction layer, so it supports lots of different types of hardware. It can run the computations either on a CPU or a GPU, and we actually support many different types of GPUs, NVIDIA, AMD, Intel. We're just about the only MD code that does support things other than NVIDIA GPUs. So part of the goal of this is that OpenMM can serve different purposes for different target audiences. So different people would use it in different ways. So first of all, you have biologists and chemists who want an MD package. They want to run simulations. And so they just use the application layer, this top level part of it, to run their simulations, much the way they would any other MD package. On the other hand, we can also target application developers, people who are writing applications of their own, but they can use the OpenMM C++ library. They can link that to their own applications and use it to add lots of different computational features to their applications. So they can use all the different forces and integration methods and whatnot that we provide without having to implement all that themselves. And finally, OpenMM is an amazingly powerful tool for algorithm developers, people who are developing new ways of running MD simulations. They can use both the Python and C++ layers, and then we have some very, very unique features I'll be talking about called custom forces and custom integrators that make it really easy to implement completely new sorts of algorithms right from the highest level, and I'll be talking a lot about that later. Of course, performance is very, very important to us. Here I have just some benchmarks, speeds in nanoseconds per day for simulating DHFR, which is a standard protein that's widely used as a benchmark for MD codes. I'm showing it here both implicit and explicit solvent using two different methods of handling long-range interactions, either the reaction field approximation or particle mesh AWOLD. I have benchmarks here for either 2 and 5 nanosecond time steps and showing both a good GPU and a good CPU. The exact numbers aren't too important, don't worry about them exactly. But the important thing here is that on a good GPU, we're getting hundreds of nanoseconds per day that we're simulating. In some cases, you're able to simulate more than a microsecond a day on a single GPU that costs about $1,000. So with pretty inexpensive hardware, you can produce really amazing amounts of simulation time. So let's talk a bit about how you use OpenMM. So the first thing to understand is that this thing that we call the application layer, it's not really an application in the traditional sense. It's a set of Python libraries. And so instead of, running an application called OpenMM and having it do your simulation, what you actually do is you write a Python script, and the Python script implements the simulation, and it does it by using these libraries. So usually when I say that, people often get a little nervous, especially if they aren't themselves programmers. And it's important to reassure you at this point, no programming experience is required. If you just want to run simulations, you can do that really easily, in much the same way you would with any other MD package. Most MD packages have some concept of a script that defines what you're going to do. It just happens that within OpenMM, that script is written in Python. In fact, you don't even have to write it yourself. We've got a really nice graphical tool that will write the script for you, just gives you a nice set of menus. You pick all the simulation options you want, and it throws out a script for you all ready to run that will do exactly what you've told it to do. So it's really easy to do that. However, you can then go beyond that. And this is why, even if you aren't a programmer, you can do really, it's worth your time to get to know just enough to be able to do some more things with it. Because the fact that you are actually creating a full Python script means that you have an amazing amount of power. You can customize it in ways that would be really difficult with almost any other MD application. So let me just walk you through a really minimal but still totally complete script. So what you see here on your screen right now is a complete MD simulation implemented in Python using OpenMM. And again, you wouldn't have to actually write the script. You can, we have this as an example that you could start from, or you could just run the graphical builder and it would output a script that looks a lot like this one. But we'll start by going through this, seeing what it does, and then I'll start showing you the ways that you can customize this and use that to do things that will be much more difficult in any other package. So let's look at the script and see what it's doing. So it starts out with a few imports. You can ignore those. All those are doing is telling the Python interpreter that we're going to be using the OpenMM libraries. Next, we have to load in the input files. And so for this simulation, we're going to start from a PDB file. So we just create a PDB file object, give it the name of the file to load, and there you go. That's all it is. It's loaded a PDB file now. We are going to select what force field we want to model this PDB file with. So in this case, I'm telling it to use the AMBER 99SB force field, the TIP3P water model. We provide a number of different standard molecular dynamics force fields that you can use. Then we tell it how we want it to model this. So we give it a bunch of simulation options, saying, for example, we want to use PME as the method of handling non-bonded interactions. We want it to use a 1 nanometer cutoff. We want it to constrain all bonds involving hydrogens. And then we tell it what type of integration method to use. So we tell it we're going to use a Langevin integrator, and we give it some options for that, like saying that it should use a 300 Kelvin heat bath, friction coefficient of 1 inverse picosecond, 0.002 picosecond time step. So now we've set all our options, and it's time to actually tell it, okay, we want to run a simulation. And you do that by creating a simulation object, and you have to tell it, okay, start our simulation from the positions that we loaded from the PDB file. And then we say, okay, we've loaded our PDB file. Before we simulate it, we should really do a local energy minimization, usually a good idea. So we call minimize energy, just one line to do this. And now we tell it we want to save our trajectory to a PDB file. And we do that by creating a PDB reporter object, adding it to the simulation. And we say, okay, save to a file called output.pdb, save a frame to the PDB file every 1,000 steps. And then we just call simulation.step and say, okay, run for 10,000 steps. And this is a totally complete functional molecular dynamics application, if you want to call it that. But let's now look at some of the ways that you could change this to do other things. So here's a really, really simple change. The previous one was running a constant volume simulation, so NVT. Maybe you want to run NPT ensemble instead, so constant pressure instead of constant volume. No problem, you just add this one extra line saying we want to add a Monte Carlo barostat to our system, we're simulating a pressure of 1 bar at 300 Kelvin. So, add that one line, and now you've got a constant pressure simulation. And this again is the sort of thing that the script builder the graphical script builder, will do this automatically. If you want, you just tell it run constant pressure, and it will know to add this line to the script. In the previous example, we started from a PDB file, but we actually can start from lots of different types of files. We can load in directly the native file formats from Amber, Charm, GROMACS, Desmond. So this example is showing how you change the script if instead of starting from a PDB file, you want to start from Amber, ParmTop, and input cord files. And so, I've highlighted here what the changes are. Really simple changes. We simply load in the Amber files at the beginning and a few other minor changes to the script just to say, okay, we're getting our topology from the ParmTop file, we're getting our positions from the input cord. So again, really straightforward things. The script builder can write all of this for you. But now let's start looking at some much fancier things that would be really hard to do in some other applications, but you can do them just a few lines of Python. So for example, suppose that you want to do a simulated annealing type simulation where you're going to start at a high temperature and then gradually decrease the temperature over some amount of time. Well, here you see a complete implementation of the simulated annealing algorithm in 3 lines of Python. We simply loop from 1 to 100. Each time through, we set the temperature to a new value that's gradually ramping down from 300 to 0 over the course of the simulation. And after setting the temperature, we tell it, okay, take 1,000 time steps, and then go on to the next iteration of the loop. So OpenMM does not have any sort of built-in simulated annealing feature. It's not an algorithm that we provide. But it doesn't matter because you don't need it. If you want to do that, here you have the whole thing in 3 lines of Python. And that's just an example of how you can build up your own algorithms very, very easily. Another example of showing some somewhat different sort of calculation. Suppose that you've actually already maybe run a simulation or run some other program that has generated a whole bunch of different structures. Maybe you use some sort of method for conformational exploration, and now all you want to do is load in a whole bunch of PDB files that you have sitting on disk, and you want to calculate the potential energy of each one. Well, here I have the complete code for doing that. So we simply say loop over all of the files in this particular directory that's called structures, and then we're going to, so Python will give us a list of every file in that directory. We are going to load in every one of them as a PDB file, and then for each one we're going to call set positions to tell our simulation, okay, I want you to use the positions I just loaded from this PDB file, and then calculate the potential energy and print it out to the console. And so this, again, in just a few lines of Python, is doing just a completely different sort of calculation. It's not running any sort of simulation, but we don't need to provide any sort of feature within OpenMM for doing this. You can write the code to do it yourself very, very easily. Now I'd like to move on to some of the quite unique features in OpenMM that make it an incredibly powerful tool for doing algorithm development. You can basically think of OpenMM as being a domain-specific language for molecular dynamics. So it's not just an application, but it's really a language in which you can create your own algorithms. And I just showed some examples of high-level algorithms, but often you need to be able to implement things at a much lower level. You need to be able to control the low-level computational kernels. And this is what custom forces and custom integrators let you do. So the idea of a custom force is that it's a way to generate forces with completely arbitrary functional forms. You just specify an expression for the energy. You just give it a string that is an algebraic expression, and it does everything else. So here I've given one line that is an example of a custom non-bonded force. So that's a type of force that it's a non-bonded interaction. So it's basically an all versus all computation. Every particle interacts with every other particle, and the energy of interaction is a function of the distance r between them. And so I've just given it an algebraic expression here for the energy of each interaction as a function of r, and that's all you have to do. Now this will run just as if it were a built-in interaction. And we have many, many of these custom forces. So custom non-bonded force is for non-bonded interactions. We have lots of other ones for other types of interactions. So here is a more complete practical example. A very common thing you might want to do in a simulation is to apply positional restraints. So you want to apply harmonic forces to particular atoms that bind them to particular locations. So those atoms can't move too far away from those fixed locations. And we'll say that we want to do it using this particular functional form. So it's just a harmonic force in, x minus x naught. So x naught is x naught, y naught, z naught is the position that you want to bind the particle to, and then it will, the force will increase quadratically or the energy will increase quadratically as it tries to move away from that. So OpenMM does not have any sort of a built-in harmonic restraint class. This is not a feature that it provides, but that's just because it doesn't need to. So here is the complete Python code to implement this. So we have this class called custom external force. And what we mean by external is that it's a force that you can think of as being externally applied to particular particles. The force on the particle is a function of just the position of that particle independent of any other particle. And so I've just given it this algebraic expression, exactly the one I showed up above. It's just a string. And then we have to tell it, oh, by the way, it includes these variables, x naught, y naught, z naught. Well, these are per particle parameters. So I am going to provide a different value of these parameters for every particle. And then we call add particle on the force to tell it which particles we want to apply this to. And so, okay, I want to bind particle 5 to the location 0, 1, negative 0.5. Okay, so we'll say add particle, apply to particle 5, and here's the value of those x naught, y naught, z naught parameters. There you all are. That's all you have to do, and now you've got a harmonic restraint. Here's showing how a custom external force might look in the context of a complete simulation script. So this is essentially the same script I showed you before, except I've added in this block in yellow. This is a different example, actually, of a custom external force. It's using it for a different purpose with a different functional form. What we're doing here is simulating a water droplet. So you've got a sphere of water, and you don't want any water to be able to just evaporate off and diffuse away to infinity. So we are applying a potential to this that's basically flat out to 1 nanometer, and then beyond 1 nanometer, it increases quadratically. So I've just given it this a string with a mathematical expression for that potential. And then we're going to loop over every particle in the system and say, add every particle to this force, meaning that we want this, this potential to be applied to every force in the system, add the force to the system, and that's it. So in 4 lines of code, we have just created this completely new type of interaction in our system. And this will now be as you run your simulation, which happens just the same way you would run any other simulation. Custom integrators are a very similar idea, but instead of defining new forces, you use them to define new integration algorithms. It is a very, very flexible and very powerful tool. It can be used to support a really wide range of integration methods. So it can do both deterministic and stochastic integrators, can be used to implement metropolized integrators. We've had users used it to implement generalized Langevin equation methods. You can do multiple time step integrators, wide range of things. And this is because it's basically in itself kind of like a simple programming language. You give it a list of the series of computations that should be performed in each integration time step. So here I've given a very simple example of velocity Verlet integrator. This is one of your most standard integrators, but you can see what the code looks like here to actually implement this with a custom integrator class, just because it's a very simple example. So there's 3 time steps, or excuse me, 3 computations that go into each time step. You first do a velocity half step, then a full step of the positions, and finally another half step of the velocities. If you look in any standard reference on integrators, you will see the equations for a velocity Verlet integrator that look almost exactly like what I've just written out here. You simply give it the equations just as strings, as algebraic expressions, and it does everything else for you. An interesting thing to note about this example here, if you look at it, the first and third uh, steps look identical, the 2 velocity half steps, but there's actually a really important difference between them. They both depend on F, which is the force acting on the degree of freedom. However, it's a different force because in that middle step, we change the positions. And when you change the positions, that means that the force on every atom will change. But you don't have to tell it that. It's smart enough to figure it out. It will just look and see, oh, I know that I've used the force before. I use this variable F, but I see that the positions have changed. I know this means that I need to recalculate the forces. And so it will do that automatically. This is just a very simple example, but it can do much more complicated things. You can have arbitrary global variables, arbitrary per degree of freedom variables. It supports various kinds of flow control with looping, conditional execution, etc. It really is basically a full programming language that you can use to describe uh, arbitrary integration methods. Before I finish up, I should say a little bit about how all of this works, because one of the things that you may have been wondering is, isn't this really slow? It's great that you can just give it an algebraic expression, but is this actually then going to run faster? Is it going to be much slower than, the built-in hand-coded ones? And the answer is that no, it actually is really fast. It runs almost as fast as any of the built-in ones. And so I just want to actually walk you through what is happening when it executes your script. So suppose you've given it this line that I show at the beginning. This is using a class called custom bond force. It's a arbitrary force between pairs of bonded particles. Again, in this case, the energy is a function of the distance between the 2 particles. So it's a function of r. So in this case, I'm using it to implement a Morse potential, which is a standard type of interaction for bonded forces. So the first thing it does is parse this expression. It runs it through a standard, algebraic expression parser, converts it into an abstract syntax tree representation. Next thing it does is to analytically differentiate this expression. So it does that. It runs it through a bunch of optimizers to try to get an efficient symbolic representation of the force acting on each atom. And so again, I'm showing you exactly what it comes up with by doing that. And finally, it takes that and generates CUDA or OpenCL source code to evaluate the force and energy. And what I've shown here is the actual source code that it generates to evaluate this. Now, I admit when you look at this, it's really, really ugly looking code. You would not write that code. It's defining a temporary variable for every single intermediate quantity, but that doesn't matter. You never actually see this. This is strictly what it uses to communicate with the kernel compiler. And if you do look at this carefully, you will see and just count the flops, count exactly what operations, what functions it's calling. You will find that it's almost exactly what you would have implemented, what you would have written if you had implemented the same function yourself. This is really efficient source code to evaluate the force and energy based on the Morse potential. And finally, it takes this and sends it to the kernel compiler. One other thing, it then takes that snippet of code, inserts it into the middle of a computational kernel, which what kernel it uses will depend on what hardware it's running on, what force type it is, etc. It compiles it. That whole process happens at runtime. So as you run the script, it takes less than a second to happen. and then this interaction runs at full speed on the GPU, just as if it were a built-in force that we had implemented by hand. So this gives you an amazingly powerful tool to implement completely novel types of interactions within your simulations, and you don't have to sacrifice performance in doing this. It runs at full speed on the hardware, just as if it had been a hand-coded, hand-implemented code. So for more information, openmm.org is the homepage for OpenMM if you want to learn more about it. We have lots of documentation there. If you're interested in taking a look at the source code, it's all open source. It is hosted on GitHub. We invite you to take a look at it. And I've given here a paper describing OpenMM and giving more information about it. So I think that is everything, and I'll be happy to take some questions now.
Great. Thank you very much, Peter. And if you have questions, there's two ways you can ask those. There's a chat function. It's in the toolbar at the bottom. It's the second icon on the right. It looks like a little caption. You can send the question to me and I can pass them on. Or if you'd like to ask it yourself and you're mic'd, there's a menu on the right, 3 buttons. If you click that, you can raise your flag and then I can unmute you and then you can just ask your question directly. So go ahead and do that. I've got a couple of questions that I can kick it off with. So could you talk a little bit about scaling? So if you wanted to run, you write up some code and you want to test an algorithm, and let's say you want to run across, I don't know, half a dozen GPUs or maybe a couple hundred cores on a compute cluster. How would you go about doing that? Do you use MPI? Do you?
No, actually. So basically, OpenMM is strictly, it runs on a single node. We do support parallelizing across multiple GPUs on a single node. But if you want to use like a whole cluster, basically you're going to be running a separate code on each one. We don't use MPI to try to parallelize a single simulation across many nodes. Most of the time, at least in the Pande group, what we're doing is we're just interested in total aggregate sampling. So by far the most efficient thing to do is just run an independent simulation on every node. That will scale far, far better than any sort of MPI-based communication to try to get strong scaling of a single simulation. You can also use methods like replica exchange, and that we do in fact have Python codes that will use OpenMM to run a replica exchange simulation across many nodes. But for the most part, our focus has just been on trying to run as fast as we can on one node.
And since you can do multiple GPUs per node, and they're so much faster, it almost
right. I mean,
obsoletes the need to run on CPU nodes.
Yeah, even at that point, scaling across multiple GPUs is really hard. If you run on 2 GPUs, it will typically be maybe 40 to 60% faster than running on 1 GPU. And this isn't just us. If you look at other GPU-based codes, I mean like Amber, their scaling is across multiple GPUs is very similar to ours. It's just really hard due to both the much greater cost of the PCIe bus, which has a pretty high latency, and just the much higher ratio of compute to communication on GPUs. So if you want to run one simulation as quickly as possible, using multiple GPUs is useful. But if your goal is just to get as much sampling as you can, even on one node, you're better off just running a separate simulation on each one.
Yeah, on that note, you mentioned it earlier in the presentation that this is one of the only packages that you can really run across NVIDIA. You can use OpenCL. You could compile for Xeon Phi. In your experience,
I don't recommend it. Go ahead.
What's that?
I don't recommend Xeon Phi.
Okay. Yeah. Do you have any so AMD versus NVIDIA? I know that AMD has some fairly compelling hardware out there now, though there's not much code, scientific code anyway, that people are running on it.
No, I recommend NVIDIA. AMD, for graphics, their GPUs are very competitive, but for general purpose computing, they really haven't been competitive. You're often looking at like maybe a factor of 2x lower than a comparably priced NVIDIA GPU. And I'm not sure why that is, whether it's just that their OpenCL implementation is inefficient, or whether it's that their hardware is less well suited to general purpose computing. But yeah, if you're looking to buy hardware specifically for running MD simulations, I would definitely go with NVIDIA.
And I guess my last question was, since people are developing and testing algorithms, and there's a lot of flexibility here, people can sort of write their own code, sort of build on examples. Is there a community around this where people are sharing some of that work, that maybe a
Oh,
Git
yeah.
repo, or and if so, where can people find that?
Yeah, so just go to openmm.org, and it's got links to various things on there. We've got a set of discussion forums, which are a good place for that. We have a page where we have links to various scripts that have been written. But yeah, just go to openmm.org.
Great. All right. With that, I think we'll wrap it up. Peter, thank you again for getting up early and giving a talk from the West Coast. We
You're
appreciate
welcome.
it very much. And thank you, everyone, for joining.
Thank you.
Bye.